If you look up at the night sky from the darkest place on Earth, you can see roughly 2,500 stars with the naked eye. Every single one of them is a neighbor, located deep within our own cosmic backyard. For centuries, humanity looked at this shimmering ceiling and assumed that was all there was. We believed our galaxy was the entire universe. Then, in 1923, an astronomer named Edwin Hubble pointed a 100-inch telescope at a faint, fuzzy patch of light known as the Andromeda Nebula. He wasn't looking at a cloud of gas. He was looking at a city of 1 trillion stars, situated so mind-bogglingly far away that its light had taken 2 million years to reach his lens. In a single afternoon, the known universe didn't just grow, it shattered. The boundaries of reality raced outward, exposing a void so incomprehensibly vast that our entire planet was reduced to less than a grain of sand on an infinite shoreline. But recognizing that the universe is big is only the first step. The real question, the one that stretches the absolute limits of human physics and imagination, is just how far that shoreline actually goes. Where does the cosmic map truly end? To understand the scale of the universe, we have to start with the only tool we have to measure it: light. We live in a reality governed by a strict cosmic speed limit. Light travels at approximately 300,000 kilometers per second. At that speed, you could loop around the Earth 7.5 times in a single tick of a clock. It feels instantaneous to our human senses, but on a cosmic scale, light is agonizingly slow. When you look at the moon, you are not seeing it as it is right now. You are seeing it as it was 1.3 seconds ago. The sunlight warming your skin took 8 minutes and 20 seconds to cross the vacuum of space. If the sun were to suddenly vanish from existence this very moment, we would continue to bathe in its warmth and orbit a ghost for nearly 8.5 minutes, completely oblivious to our doom. This delay creates a profound consequence for how we view the cosmos. Every telescope we build is not just a magnifying glass, it is a time machine. The deeper we look into space, the deeper we are looking backward in time. If we zoom out past our solar system, the kilometers become uselessly small. Instead, we measure distance by how far light can travel in a single year, a unit known as a light year, which equates to roughly 9.5 trillion kilometers. The nearest star system to us, Alpha Centauri, sits about 4.2 light-years away. If you boarded the Voyager 1 spacecraft, which is currently screaming out of our solar system at over 60,000 kilometers per hour, it would take you roughly 75,000 years to reach it. And yet, on the scale of the universe, Alpha Centauri is practically close enough to touch. Our local neighborhood is the Milky Way galaxy, a majestic, swirling spiral of over 100 billion stars. To cross it from one edge to the other would take a beam of light 100,000 years. If you were to shrink the entire Milky Way down to the size of a grain of sand, the observable universe would still be larger than a double-decker bus. This brings us to a vital distinction that modern astronomy must make when answering how big the universe is: the difference between the universe we can see and the universe that actually exists. The observable universe is a spherical bubble centered precisely on you. More accurately, it is centered on anyone, anywhere, who looks up at the cosmos. The edge of this bubble is defined by a hard boundary called the particle horizon. This horizon represents the maximum distance from which light has had enough time to travel to us since the dawn of creation. Because the universe began roughly 13.8 billion years ago, your immediate intuition might suggest that the observable universe must therefore have a radius of 13.8 billion light-years. It is a perfectly logical assumption, but it completely ignores the defining characteristic of our reality: the universe is not static. It is expanding. In the late 1920s, Edwin Hubble made another groundbreaking discovery. He noticed that the light coming from distant galaxies was shifted toward the red end of the electromagnetic spectrum. In physics, this is known as a Doppler shift, or more specifically, a redshift. It happens because the space between those galaxies and our telescopes is stretching. The light waves are literally being pulled apart as they travel through the vacuum. The universe is not expanding into anything, rather, space itself is growing. Imagine drawing dots on a deflated balloon and blowing it up. The dots don't move across the rubber between them stretches, causing every to move away from every other. Because space has been stretching for the last 13.8 billion years, the objects that emitted the light we see today have moved much further away from us since the moment those photons began their journey. When we calculate this cosmic expansion, we find that the radius of our observable bubble is not 13.8 billion light-years, but roughly 46.5 billion light-years in every direction. This means the total diameter of the observable universe is a staggering 93 billion light-years. To grasp what is contained within this 93 billion light-year bubble, we have to look at the large-scale structure of the cosmos. Space is not a chaotic, uniform soup of stars. It possesses an intricate, almost biological architecture. Galaxies are bound together by gravity into groups and clusters. The Milky Way belongs to the local group, a collection of about 54 galaxies. These clusters are, in turn, packed into colossal structures called superclusters. Our local group is merely a tiny appendage on the outskirts of the Laniakea supercluster, a cosmic network containing over 100,000 galaxies spanning 500 million light-years. When you zoom out even further, to the very edges of our observable bubble, superclusters begin to look like thin, glowing threads. This is the cosmic web. Colossal filaments of matter, burning with the light of trillions of stars, separated by immense, dark expanses of absolutely nothing known as cosmic voids. These voids are vast, empty deserts where not a single atom of matter can be found for hundreds of millions of light-years. Within this observable bubble, scientists estimate there are up to 2 trillion individual galaxies. Each galaxy houses hundreds of billions of stars, and modern exoplanet data suggests that most of those stars host worlds of their own. The sheer volume of matter is staggering. Yet, the most humbling realization of modern astrophysics is that this entire 93 billion light-year web of light is just the prologue to a much larger, darker story. What lies beyond the 93 billion light-year boundary? What exists outside the edge of our observable bubble? The short answer is, more universe. If you were to instantaneously teleport to a galaxy sitting right on the absolute edge of our observable horizon, 46.5 billion light-years away, the view wouldn't look like the end of the world. You wouldn't find a brick wall, or a cosmic drop-off, or an empty void. Instead, you would find yourself at the exact center of your own new observable bubble. You would see cosmic filaments, superclusters, and voids stretching out in every direction around you. But back on Earth, the regions of space you just left behind would now be entirely invisible, buried beneath your new horizon. We know there is matter beyond our view because we can see the cosmic background radiation, the fading afterglow of the Big Bang, flowing uniformly from all directions. There is no edge to the matter we can detect. However, because of the expansion of the universe, we are actively losing the ability to ever see what lies beyond. In 1998, astronomers studying distant Type Ia supernovae made a discovery that shocked the scientific community and fundamentally altered our understanding of the future. They expected to find that gravity was gradually slowing down the expansion of the universe. Instead, they discovered that the expansion is accelerating. Something is pushing the fabric of spacetime apart faster and faster as time goes on. Physicists call this mysterious force dark energy, and it makes up roughly 68% of the total energy density of the universe. We do not know what it is, but we can see its terrifying effects. Because the expansion of space is accelerating, the distance between widely separated galaxies is growing at an ever-increasing rate. At a certain distance, the space between two objects is expanding so quickly that the gap increases faster than the speed of light itself. This does not violate Einstein's theory of special relativity. Relativity dictates that no object can travel through space faster than light. However, relativity places no such limits on space itself. Space can stretch at whatever speed it pleases. The consequence of this is bleak. Galaxies that are currently situated beyond a certain threshold are receding from us faster than light. The light they emit today will never, ever reach our planet. The space between us is growing too fast for the photons to bridge the gap. They are trapped on a cosmic treadmill, running toward us but permanently slipping backward. Right now, we are experiencing a slow, invisible cosmic divorce. Every single year, thousands of galaxies cross this invisible threshold, passing out of the reachable universe forever. They fade into the dark, becoming completely inaccessible to any future civilization, no matter how advanced. We are living in a golden age of astronomy, where the wider universe is still visible to us. In the deep, distant future, the expansion will have carried all other galaxy clusters so far away that the night sky from Earth will be completely black, devoid of any external light, leaving future astronomers to believe they are entirely alone in an empty void. If the real, total universe extends far beyond our 93 billion light-year bubble, how can we possibly measure something we are fundamentally forbidden from ever seeing? The answer lies in geometry. By analyzing the shapes and patterns within our observable bubble, we can deduce the shape, and ultimately the size, of the entire cosmic tapestry. According to Einstein's theory of general relativity, matter and energy warp the fabric of spacetime. The total mass and energy contained within the universe dictates its overall geometric shape. Cosmologists recognize three theoretical possibilities for the geometry of the universe: closed, open, or flat. A closed universe occurs if the density of matter and energy is exceptionally high. In this scenario, gravity is strong enough to curve spacetime back in on itself, creating a three-dimensional shape analogous to the surface of a sphere. If you were to get into a spaceship, point it in a perfectly straight line, and fly long enough in a closed universe, you would eventually loop all the way around and end up right back where you started. A closed universe is finite. It has a measurable volume, even if it has no physical edge. An open universe occurs if the density of matter and energy is too low. In this case, space curves outward like the surface of a saddle. The geometry is distorted in a way that causes parallel lines to diverge over time. An open universe is infinite, extending forever in all directions without end. The final possibility is a flat universe. This occurs if the density of matter and energy hits a very specific, precarious value known as the critical density. In a flat universe, spacetime has no net curvature. Parallel lines remain perfectly parallel forever, just as they do on a standard flat piece of paper. Like an open universe, a perfectly flat universe is mathematically infinite. To determine which of these three shapes describes our reality, scientists turned their instruments toward the oldest light in existence, the cosmic microwave background, or CMB. The CMB is the thermal blueprint of the infant universe, imprinted on the cosmos just 380,000 years after the Big Bang. It is a map of incredibly subtle temperature fluctuations. Because we understand the physics of the early universe with immense precision, we know exactly how large these temperature fluctuations should physically be. By measuring the apparent, angular size of these hot and cold spots on the sky, astronomers can perform a cosmic version of basic high school trigonometry. They can shoot two straight lines of light across 13.8 billion years of history to see if those lines bend. If the spots appeared larger than expected, it would mean space is positively curved like a sphere, magnifying the light. If they appeared smaller, space would be negatively curved like a saddle. When satellites like WMAP and the Planck Space Observatory mapped these fluctuations with unprecedented accuracy, the results came back with astonishing clarity. The spots were exactly the size they should be. The lines of light did not bend. Within a tiny margin of error of less than 1%, our universe appears to be perfectly, undeniably flat. This brings us to the precipice of a mind-bending conclusion. If the universe is flat, and if it is uniform in its structure, then the total universe is not just big. It is infinite. It is a concept that the human brain is fundamentally unequipped to handle. We live in a world defined entirely by boundaries. Every object we touch has a beginning and an ending. We understand journeys because they have destinations. But an infinite universe possesses none of these luxuries. If the universe is truly infinite, it means there is no center. Every point in space can claim to be the center, because there is an endless expanse stretching away from it in every direction. It means that if you traveled forever in a straight line, you would never run out of space, you would never run out of galaxies, and you would never reach a final wall. Even more disturbing are the philosophical implications of an infinite, flat universe. Every object within our universe, be it a star, a planet, or a human being, is made up of fundamental particles arranged in a highly specific configuration. Within any given finite volume of space, such as our 93 billion light-year observable bubble, there are only so many ways you can arrange those particles before the laws of quantum mechanics dictate that you must repeat a combination. Think of it like a deck of cards. There are a massive number of ways to shuffle a deck, specifically 52 factorial, an incredibly large number. But if you shuffle that deck an infinite number of times, you will eventually repeat the exact same sequence. You will do it multiple times. In fact, you will do it an infinite number of times. If the universe is infinite, and the matter distributed within it is uniform, then every single possible configuration of matter must repeat. This means that out there in the dark, far beyond the light of our observable horizon, there is another galaxy identical to the Milky Way. Within that galaxy, there is an identical solar system, with an identical planet Earth. And on that Earth, there is an identical version of you, sitting in the exact same room, reading these exact same words, thinking these exact same thoughts. And they are not alone. There are infinite versions of you. Some are living out this exact day, while others are experiencing a day where you made a slightly different choice, walked down a different street, or chased a different dream. Every timeline, every possibility, every variation of history would not just be a theoretical concept, it would be a physical reality existing somewhere out there in the endless expanse. Of course, science must always maintain a strict boundary between what is mathematically probable and what is definitively proven. We cannot say with absolute, infallible certainty that the universe is infinite. We can only state what our measurements tell us. Because our data has a tiny margin of error, there remains a small possibility that the universe is not perfectly flat, but possesses an incredibly minute, almost imperceptible positive curvature. If that is the case, the universe would not be infinite. It would be a colossal, closed hypersphere. But even under this finite model, the scale is staggering. If the universe is closed but appears as flat as our instruments suggest, physicists calculate that the total universe must be, at an absolute minimum, 250 times larger than our observable bubble. That means the total universe would span at least 23 trillion light-years across. It would contain trillions of entire observable bubbles just like ours, completely locked away from our view, separated by horizons of expanding space that no telescope will ever pierce. We find ourselves stranded on a tiny island of light in a sea of absolute infinity. We are a young, fragile species that only recently figured out that the stars are distant suns. We have spent our entire history confined to a single rocky outpost orbiting an ordinary star in the quiet suburbs of a typical galaxy. Yet, despite our profound insignificance, we have managed to look out into the dark and deduce the rules of the cosmos. We have weighed the stars, mapped the ancient radiation of creation, and measured the very geometry of spacetime itself. How big is the universe? It is large enough to render our existence entirely meaningless on a physical scale. But it is also large enough to hold everything that ever was, everything that ever could be, and everything we have yet to discover. The map stretches out forever, and we have only just begun to look at the shoreline.